So here we have two number of islands problem, 1 and 2. So let's jump right into it. So given a 2D matrix and 0 stands for the sea and 1 stands for land, and if two land is adjacent, we consider them to be on the same island, and we don't consider diagonal, so only consider that uh, two when they share the same sides and want to find the total number of islands. And for example, right here we have 1, 2, 3. Okay. So right off the bat for this problem, it looks pretty simple. I separated it into three components. First, we loop through the entire matrix, row by column, and then at each point we traverse from it if it's a land, and we mark every land that is connected to it as visited. So next time, for example, encounter this one right here, it won't double count. And we repeat this same procedure for the entire map, and that should give us the number of island. And so the first component we cover is the loop through of the entire matrix. And the second component is once we reach a land that's unvisited, we sort of traverse from that and mark every land that is connected to it as visited. And also the third component, you just a helper function that help you check three things to see if a land is a valid point. First, it has to be inbound, so it has to be bigger or equal to 0 index-wise and shorter than the length or the height accordingly. And also, it has to be not in the visited, otherwise we will double count and it will mess up our total number of islands. And third, it has to be a land. It cannot be a sea. If it is a sea box, we'll just ignore it. So let's start writing the code. So we start off with the sanity check, and if not grid, we will just return 0. So just ignore that, and for length of grid, and n for the width of the grid, and m for the length of the grid. Either way, it doesn't really matter. And here comes the loop through of the entire matrix as we talked before. And for that, we need to specify our visited set and our number of islands. So this is the return result. The initial value, the default value is 0. So, and we want it first to the spot like we mentioned before. First, it has to be a 1, and second, it has to be unvisited. Otherwise, it may be visited by a previous one. So if grid ij equals 1 and the point ij is not in visited, there we go, then we will either run BFS or DFS. We'll do both, and here we'll just start off with BFS. So we'll throw in the grid, the IJ, and the visited set. And after this, we will essentially, for example, if we start here, we should either use BFS or DFS to reach this point and this point. So we will have the island increase by 1, and at the end we will return the island. There we go. And let's jump right into the meat part. So BFS, and let's call it X and Y, and visit it. Since it's a BFS, we will import deck from collection. Also, we want the 4 directions that we can possibly check for neighboring land. So directions equals to 1 0 minus 1 0 0 1 and 0 minus 1. Okay, and like we said before, we have to update the visited. So after we set up the queue, so the initial value on the queue would be the first starting point right here. And we don't have the grid. And then we will add the point to visited. And then we'll do the standard BFS procedure. So while queue, the current node is equals to queue.pop left, then we will check the 4 directions for D, X, DY, and directions, and new X equals to X plus DX, and NY equals to Y plus DY. And at this time, we have to check if the point is valid, and it has to satisfy this 3 condition we mentioned before. They are, first, it has to be inbound. It cannot go outside of this red area, and also it has to be never visited. And third, it has to be a land, otherwise it would just be sea and it cannot form an island. So if it's not valid, we'll continue, we'll skip that. And then we come to valid part. So since it is valid, means that it's never visited, and it is a land, and it's inbound, we will add that to our queue. And also, we will mark it as visited. Since what we're trying to do here is simply the marking of the visited set, it doesn't really matter what we return, we'll just return nothing here. And then to finish our helper function, first we have to check for inbound. Actually, let's check for visited. It's faster. If it's in visited, we'll return false. And second, check for inbound. If not, so 0 less than or equal to x less than m will less than or equals to y and less than m. And we'll define m and n here, and equals the length of the grid, and m equals to length of the grid at that row. If not, inbound will return false. And third criteria we have is return if grid is a LAN. So that should be the basic skeleton of the code. And let's do a quick sanity run through. So if not grid, return nothing, so no island. And this is for the height, and this is for the width of the grid. And we set up our visited set, and we set up the initial default value of island. So it start up with 0, and we move through the 2D matrix row by column. And if it is a LAN, we start our tiny search to make sure every LAN that is connected to it in the 4 directions will be marked as visited. So then we do BFS in this version, and island plus equal to 1 looks correct. And this is the basic BFS part, and with one little caveat being we have to keep track of our visited set here, and Q equals to deck. This is our initial point to start from, and mark that as visited. And while Q, we pop it off and we check all 4 directions, and if the point is valid, it will go here, and we will add the point to the queue, so we can start our new search of 4 directions from there, and we have to mark it as visited as well. And the visit is valid part consists of 3 checks. First, it has to be not in the visited. Second, it has to be inbound. And third, it also has to be a LAN. So let's run a quick check. So, there's a typo. So apparently I misspelled grid. So it's GERD here, grid. Let's check for other grid. So line 14 apparently also misspelled grid. So there's a problem here, and let's try to figure out, let's try to debug this. So since we are having more island than expected, means that we're not marking as much visited as we needed. So LAN not in visited, and let's see here. So we first have our queue, and it's deck, and then we add the current point to visited, while Q node equals to pop left looks correct. And here comes the 4 directions. There's the problem. So it should be, oh, it's not, it's correct. NX equal to X plus DX, correct. And Y, new Y equals to Y plus DY, also correct. And if not, self dot is valid, grid new X, new Y visited. If it's not valid, we just go to the next direction. And then Q dot append new X, new Y, visited dot add new X, new Y. Let's see, and check for the is valid part. If it's visited, we return false. And if it's not in this range, return false as well. And return grid looks correct. And let's see. If not, self dot is valid, grid, and x and y. So we're not adding as much visited as we need to. So here we have visited with add x, y, and here have new x, new y. So here we mark as 5 instead of 3. Let's see. Let's be patient and do another run through. So if it's not grid, return 0, and n and m, pretty standard, and visit it as a set, and island the return value, and we move through the width, and then we loop a width through the height, and we loop through the width. And if I and j is a LAN and has not been visited yet, we'll do a BFS search on it with grid I, j, and visited. And after all this, we will update the island, and at the end, we'll return the island. Let's jump to the BFS part. So we have queue. We set up with deck structure, and initial value, it is default starting point, and we add that to visited. Or let's see, we don't really have to add visited after this line because everything that is in the queue will be covered by this line, and the initial point will be covered by this line. So let's see, node equals to I see the problem. So it is not node. We didn't connect node with xy here. It always the xy here. So that's where the problem is. Got him. So xy equals to q dot pop left. So here, and it should be correct this time, and it is. Here we go. And like I promised before, we will do another version with DFS. So let's do that as well. Self.dfs. And this time, our input would be rather similar. But let's comment out the DFS part. The is valid should stay the same, and let's do the DFS one. DFS self grid xy visited, and first step will add xy to visited, and we will go through 4 directions for dx, dy, and directions. And like before, we check for the validity of the input. If not, self dot is valid. It will be grid. Unlike in DFS is a recursive process, so it is fine for us to just use X and Y since it is updated every single time. Before, the mistake we made was instead of the X and Y every time, we had it as node. So we have linked the current pop item from queue to the new index. So we check for the validity of the new points with all this input. And if it's not valid, we continue. Oops, continue. And if it's valid, then we will do a DFS on it. So self.dfs, like I mentioned before, it is a recursive process, grid being the same, and x being nx, and y being ny, and visited is still the same. And let's run through logic here, and everything up to here should be the same. We go through the 2D matrix, and we at each point, instead of BFS this time, we use DFS to render every connected LAN around it to be visited. So visited, mark it as visited, and for the 4 directions, we get 4 new directions, and we check for the validity of the new points, and if it is valid, we do a new DFS on it. Now let's do a quick check, and it works, and let's submit it. Okay, it also works. And let's talk about the time complexity and space complexity. So for space complexity, what extra data structure are we utilizing? For DFS, we're not using a whole lot of data structure beside this visited set, and in the worst case scenario, it will be the entire 2D matrix. So if it's n by n, it will be of space n times m. And for time complexity, since at each point we are doing a search, but the thing is, the max we're gonna get is actually just all of n times m, because if, for example, start from this point, we go through all the points here, and at the next step we will not have anything left to visit, so m times m is the max we can visit. So the time complexity will be big O of m times m. And that is this problem. And let's jump to the second problem. So the second problem is a little bit trickier. So like before, we're given a 2D matrix. However, this time we're also given an array of points. And at each point, we will flip the originally old C matrix, and at that point we'll make it a LAN, and the result we want to get is a sort of streaming result that at each point what's the number of island. So for example here, originally it is a 4 by 5 C, and the first input is 1 by 1, so we'll flip the point 1 and 1 to be 1, and the current number of island is self-explanatory 1, and 0, 1, and can see is connected, so it is still 1, and 3, 3, and 3, 4. and as we expected, the output will be 1122. So let's do a little bit of brainstorming here. We can definitely do BFS or DFS, but keep in mind that with DFS or BFS, we sort of have to do it in one direction. For example, from this point diagonally to the lower half, the lower right of this point, and we want to we want to have this sort of connection info at hand at all time to see if the newly introduced LAN has connected to previous LAN. For example, if these two, if let's draw the graph here. If this two was original LAN and this point right here is 0, with the introduction of this new LAN, we will originally have 1, 2 number of LAN, and with this new introduction of LAN, it will actually decrease by 1, and this 3 LAN will become an island. And that's where the method of union find comes in. With union find, we get to track the sort of the fodder or the token spot of an island at all time, and by that we can see if two land is actually an island or in an island, or if with the new introduction of a new land we will connect it to previously disconnected land, and the size would be the current number of island. This is for the output purposes, and the previous operation, like here, since inputs operators, and the result, and it will be separated into three components. The first component is the main component. Here we sort of just do some validity check and to see when we should call the union function. And in union function, basically we connected two previously disconnected points because they belong in one island. And what we have to update first is the fodder or the token of the island and the size of the current number of island. And also in find function, which we will call in union, we will find the root of the island or the token root of the island, and at the same time we will sort of do this compressing operation that have everything on the route to and make it its token to be this root token. And I'll show it in a quick I will show it later to see how we actually gonna do that. And the benefit of doing this is that now when we call we're trying to check the token of any of this land in this island, the token will be this node right here, and we will set up this token to be itself. So all four nodes here, their token is actually the same, and by that we can know that they are actually in the same island. And we can run a quick example to see how this will actually work. For example, we start off by loop through the 2D matrix and start with here is not a LAN, and here is a LAN, and we have size 1 from 0. We plus it, add it by 1, and we go through here, no LAN, until we reach here, and the LAN will increase by 1 since we now have 2 land. And then we have to check if it is connected to any other land. And it is. Out of the 4 position, one of them is a land, and we will actually decrease the size by 1 since these two are now one island. And the same goes for this component right here. From here, we will have 2 islands. So this one and this one. We have not reached this guy right here. And at here, first we will increase it by 1, and same goes for here, increase it by another 1, and one here. So even though we have 3 land here, we only increase the island size by 1. And this loner right here, we also add a 1 to it. And let's jump right into the code section. So first, we will set up our return value. And then, like before, we can actually call it token. And it will be a map. And we will also have a size to track at all time. It will start off at 0. And we also have previous operator. And this will be we can make it a set or a list. It doesn't really matter that much. And for operator in operators, and we'll have x to be the operator dot x and y to be operator dot y. And if xy is in previous operation, means that we have flipped that spot already, so nothing to be done. So we will have the result append, so size, and then continue to the next place. And if the flipping has not occurred previously, we will now try to set up its token and size. So the self dot token, the current would be itself. And we'll explain, like we explained before, by doing this, we can actually know that this is the token. And then self.size plus equal to 1. Of course, we have a new land. And now we want to check the 4 directions to see if we can sort of encounter any other lands. Let's just copy it from here. And for dx, dy, and directions, and nx equals to x plus dx, and y equals to y plus dy, and if nx and y and previous operation means that the current land is actually within the same island as the previous land, and we will do a union operation between the 2 points. And after the 4 operations, we will reach potentially 4 other land, and we will update the token and the size accordingly. And after all that, we will append that to the result, and at the end we'll return results. And there's a typo here. self.size, since it is a global variable, and then we'll set up our union function. So, and point A and point B. And first we will do a find procedure. Root or token A equals to token A equals to self.find A. Token B equals to self.find B. And like I said before, if they share the same token, means that they are already in the same island, so no update is needed. However, if token A is not the same as token B, but since it came in from here, which implies that they should be in the same island, then we have to do something about it. The first step, of course, we have to reduce the size by 1. Since now we have 2 individual land that are double counted, we'll reduce this by 1, so we have 1 island. And also, we want to make sure they have the same token because they're in the same island. Then we can do it either way, but the way I chose to do it here is actually just make the token of A to be B. Either way, it doesn't really matter. And at the end, that's it for union. Now we'll work on the find function. So what find do is first compressing all the node on the way to make sure they all share the same token as the token itself. And first, we want to get to the token to see what's the token of the island that A is in. So we'll set up our path. This is for recording all the nodes in the path through the token node. So while A is not equals to self dot, so while self dot token A is not equals to A itself, the reason why we do this is because when the token of a node is equal to itself means that it is the token of the island. So if it's while it's not equals to that, it means that we still have to clean up to see what the actual token is. We will first append the node to the path so we can update its token later, and then we have to update itself to its token. So we're climbing up and compressing, and then once we get out of this loop, we will reach a node that its token is itself, so we'll reach the token node. And then for P in path, we want all of the token here to be the token that we end with. So token P equals to A. And at the end, we will return the current token node, which is A. So this thing that we exit out of this node. So let's do a quick sanity check since this is a rather complicated code. So first, we set up our default data structures. We have the result for return value. We have the token. So as a map. So for each node, we can get what's the token of that island that the node is in, and we have the size, the current size of how many island that there is, and the previous operation. And then first we loop through all the operators and get the two positions. If it's already been flipped, we just append the result and continue. And if it has not been performed before, we will set its token to itself, and then we'll add a size by 1. And then we'll check the 4 directions, and if one of them has been flipped, we'll perform the union operation because they belong in the same island. And then after checking the 4 directions, we will append the result and return. And then we look at the union function. First, we find the current token of the island that A is in, and same goes for B. And if they're not the same, but in fact they should be the same, so we deduce the size by 1 and we set the token to be the same. And then we'll do the find operation. Like before, we're doing a compressing of the token here. Basically, what compressing means is that we want to make sure that every node in this island share the same token. We don't have to go up like a linked list structure. We want it to be a star structure. And so while self.token A is not equal to itself, and by itself it means the token node itself, then we append it to path so we can update it later, and we climb up in level, climb up a level until we reach the token node, and that's when we will jump out of this while loop, and then we will set everything in the path to have the same token as the token node, and at the end return the token node. And let's try to test it. And there is actually an error. So 1, 2, 3, 4. So there's something wrong with our update. Let's see where it actually could be. So apparently we're not subtracting it correctly. What we have here is just 1, 2, 3, 4. It adds up. So we find the token of A and B, and if they're not the same, we'll reduce it by 1. Let's see. If now in previous, I do these two together, and result.append self.size. So this line is not performing, means that they're actually the same, which they should not be. Let's actually go through the entire code. Result and token and self.size, previous operation. Oh, so we're not updating the previous operation set. So previous operation dot add x, y. And let's see how that turns out. There we go. It is correct. So the problem was we're not updating the previous operation set. And as for the time complexity, you can see here, assuming these are constant time, or um, assume they're constant time, we will have a big O runtime of the length of the operator, since we have a one single loop here, and this guy is just length of 4. So assuming the length of the operator is k, we will have a runtime of O of k, and it also depends heavily on what's the runtime of union. And fine. So that's it for the number of island 1, which is a simple traversal problem. We did it in two fashions. The DFS way and the BFS way is pretty simple, and it is an easy question. And for number island 2, it is a little bit harder, and we utilize the union and find algorithm, and that's it.